those who have joined the class may give their attendance in the chat box. I repeat, those who have joined the class may give their attendance in the chat box. Okay, it is 3:15 p.m. I will not wait further. Just give me a minute so that I can present my screen. Can anyone confirm me whether my slides are visible or not?
Yes, sir, visible.
Okay, thank you. So, good afternoon to all of you. If you remember, in the last class, I will give you just a recap of what we have did in the last class. In the last class, we have started our discussion with fatigue failure. We did one experiment called this rotating beam fatigue testing machine. In this experiment, what we found out? We found out the endurance limit of the component. If any component is given to you, if that component is, if you want to fail that component by fatigue failure, then what you need to determine? You need to determine the endurance limit of that particular component. So determination of that endurance limit we did with this particular experiment, and this experiment is known as rotating beam fatigue testing machine developed by the scientist called R.R. Murray. If you remember, from this experiment we can generate a graph, and that graph is known as SN diagram or Euler diagram. What does this graph tells us? In this graph, along x-axis there is number of cycles, and along y-axis there is a stress amplitude. Both the graph are plotted on a log paper. That means number of stress cycle is also in terms of log, and number of stress amplitude is also in terms of log. That is log base 10, not base e. So log base 10 of n and log base 10 of SF. From this graph, from this experiment, we concluded that when the number of stress cycle is 10 to the power 6, when the number of stress cycle is 10 to the power 6, that means 10 lakh cycles. That means when you have rotated this specimen for 10 lakh times continuously by the application of fluctuating load, then what happens is that at 10 to the power 6 cycle you get one stress value, and from that particular point the stress value is constant and is parallel to x-axis. So that particular point from where you are getting a constant stress value, even if you increase the number of stress cycle, that particular value along y-axis is known as endurance limit stress. That means this particular point is your endurance limit point and is given by log base 10 SE. I have told you that in the last class that we denote endurance strength by the symbol called SE. So this particular point, that means this is my y-axis. From the y-axis, if I measure this particular distance, This vertical distance, this will be how much? This will be log base 10 SE equal to something. So your that SE value will be anti-log of that something value. Is it clear? Hello?
Yes, sir.
Fine. So from this particular experiment, what we found out? We found out the endurance limit present in the material before the appearance of first fatigue crack. Now, if you see in this SN diagram, it is starting from 10 to the power 3 cycles. This is log base 10 n, that is 3, 4, 5, 6, 7, 8. It is not starting from 0 0. It is not starting from origin, and this particular graph is applicable for steels. If you want to draw the stress strain diagram of steels, that starts from 10 to the power 3 cycles. Fine, but normally SN diagram starts from origin. It starts from origin and it goes till 10 to the power 8 cycles. So we can divide this SN diagram into two regions. One region is called low cycle fatigue and the second region is called high cycle fatigue. One region is called low cycle fatigue and the second region is called high cycle fatigue. This is your origin. Along x-axis you are having number of stress cycles and along y-axis you are having stress amplitude. Both are plotted on a log paper, that is log base 10n and log base 10 SS. Fine. So if you want to draw specifically SN diagram for steel, then this particular line will come over here. That means it will start from 10 to the power 3 cycles. This is stress SN diagram for steel. But for a general material, the SN diagram starts from 10 to the power 0 cycle and it terminates till 10 to the power 8 cycle. So we divide this SN diagram into two regions. One region is called your low cycle fatigue and another region is called your high cycle fatigue. Any fatigue failure when the number of stress cycles are less than 10 to the power 3 cycles or less than 1000 cycles, then that particular failure is known as low cycle fatigue failure. That means this is your low cycle fatigue region. Any fatigue failure when the number of stress cycles are more than 10 to the power 3 and is up to 10 to the power 8 cycle, then that particular SN curve is known as high cycle fatigue. Where you get the endurance limit stress? You get the endurance limit stress at in high cycle fatigue region, because at 10 to the power 6 cycle fatigue phenomena is observed in the specimen from that particular experiment, and from this particular point only the stress value will be constant till 10 to the power 8 cycle. In low cycle fatigue you don't get any kind of endurance limit stress. Is it clear, the difference between low and high cycle fatigue? Any doubt in this low cycle and high cycle fatigue?
No, sir.
Okay. Next. Next topic is notch sensitivity. So can anyone tell me by the name of the topic what it can be? Notch sensitivity. What do you mean by the term called notch sensitivity?
Sir, the value at which the notch starts working, I think.
Notch sensitivity. What is sensitivity? In general, if I want to define that my ear is very sensitive, by that word, what I understand? My ear is very sensitive. By that word, what I understand?
It can
Sir,
pick
that
up
means,
very low volume sounds as well.
Sorry?
sir, the response time will be very much less.
Yes, for example, if say if you are standing in front of me and if your ear is very sensitive, if I am talking something, definitely you will hear, but you will hear say after time t equal to 2 seconds, after time t equal to 4 seconds, after 1 minute, yes or no?
Yes, sir.
Similarly, in a material, if you make a small notch, in the same material, if you make a big notch, which notch will be sensitive to fatigue failure? The bigger notch or the smaller notch?
It's a bigger notch, I think.
Definitely the bigger notch, because the material will try, the entire component will try to get break into two pieces from that bigger notch portion, because that bigger notch is portion is highly stressed region than that of the smaller notch region. This is the physical definition of notch sensitivity. Now it is clear what is notch sensitivity. Hello.
Yes, sir.
Yes, sir.
Fine. For example, assume I'm having one material. Fine. If this material is subjected to fatigue loading, say you have made one notch over here, you have made a second notch over here, you have made a third notch over here. Definitely, the fatigue failure will take place from this notch also, from this particular notch also, but from this particular notch also. But the highly stressed region will be which region? Will be the region near to notch 1, or it is the region near to notch 2, or it is the region near to notch 3?
Notch 3, sir.
The region near to notch 3. That means in fatigue, the component has a tendency to get breakdown quickly near the region of notch 3. That means notch 3 is much more sensitive than notch 2 and then notch 1. Is it clear?
Sir, so basically notch sensitivity is how easily the notch undergoes fatigue failure.
Yes, but that will depend. That will depend if you are making a notch of 2 mm depth, if you are making a notch of 4 mm depth, if you are making a notch of 10 mm depth in a 30 mm depth specimen, and definitely that 10 mm notch depth will be much more sensitive to fatigue stresses than compared to notch 1 of 2 mm depth and notch 2 of 5 mm depth. Yes or no?
Yes, sir.
Fine. Okay. So this is a physical definition of what notch sensitivity is all about. But before defining notch sensitivity, let us understand this term. What is this term? This term is known as fatigue stress concentration factor, denoted by symbol KF, denoted by symbol KF. Likewise, stress concentration factor, if I am having a component, if that component is undergoing a fatigue, there will be one fatigue stress concentration factor, and that is defined as the ratio of endurance limit of notch free specimen divided by the endurance limit of notched specimen. That means when the specimen is not subjected to any kind of notch, what is the value of endurance limit? Divided by when the component is subjected to notch. That means when you have made a notch in the specimen and you want to see how that material is failing in fatigue. At that time, what is the value of endurance limit? You take the ratio, you will get the value of Kf, that is fatigue stress concentration factor. Is it clear?
Yes, sir. Clear, sir.
Okay. So it is, see, this fatigue stress concentration factor is applicable to actual material and depend upon the grain size of material, because for an ideal material there will be no notch, grain size will be uniform throughout, but if you take an actual material, never the grain size is uniform. I think this you might have studied in material science, yes or no?
Yes, sir. There are always irregular
If you
surfaces.
take an actual material and if you see it with the help of microscope, there will be discontinuity in that material. Maybe that discontinuity is very small or it is very large. So if there is a discontinuity, even if a small discontinuity will change the grain size of the material. Fine. So this Kf is dependent on actual material and the grain size of the material. Now I can define notch sensitivity as it is the tendency of a material unable to resist the damaging effects of stress raising notches in fatigue loading. Again, I am repeating, notch sensitivity is defined as the tendency of a material unable to resist the damaging effect of stress raising notches in fatigue loading. The definition is exactly similar of what I have explained you. How much the notch is sensitive to fatigue loading and how less a notch is sensitive to fatigue loading. Okay. Any doubt so far? Hello.
No,
No,
sir.
sir. No
No,
doubt.
sir.
Fine. Likewise, now if you want to measure this notch sensitivity value in actual material, how you can measure? You can measure by a term called Q, and that Q is known as notch sensitivity factor. You can measure how sensitive the notch is in a material. You can measure it by a term called Q, and that Q is known as notch sensitivity factor. It is defined as the ratio of increase of actual stress over nominal stress divided by increase of theoretical stress over nominal stress. And how to get the value of Q? There is a relation between Kf, that is fatigue stress concentration factor, and this notch sensitivity factor. What is that relation? That will come from this particular definition, that is increase of actual stress over nominal stress. We know what is a nominal stress. Nominal stress is that stress value that we find out from the concept of strength of material. For example, if a body is subjected to bending moment, then the nominal stress will be what? It will be the bending stress, that is m into y by I. If a body is subjected to tension, then the nominal stress is what? Nominal stress will be tensile stress sigma t is equal to p by a, and so on. Fine. So first of all, what we will do, we will find out the value of nominal stress, we will find out the value of actual stress, then we will find out the value of increase of actual stress over nominal stress. How we can find out? Definitely the value of actual stress will be more than that of the nominal stress, because in actual stress we have to take the actual conditions. So the increase in the stress will be actual stress minus nominal stress. That will be the increase of actual stress over nominal stress. Similarly, in the same fashion, I will find out the value of increase of theoretical stress over nominal stress. I will take the ratio and I can get the value of Q. And there will be a relationship between Q and Kf. Is it clear? Hello.
Yes, sir. Yes.
Okay, so let us find out the value of nominal stress first. Let us assume that sigma naught is what? Sigma naught is nominal stress obtained by elementary equations. Elementary equations are those equations which we use from the concepts of strength of material. Now, when a component is subjected to fatigue loading, definitely this fatigue stress concentration factor will come into account. Likewise, stress concentration factor, I know that stress concentration factor is given by what? It is given by Kt is equal to maximum stress divided by nominal stress. Similarly, fatigue stress concentration factor will be what? Endurance limit, maximum endurance limit divided by maximum endurance limit when there is no notch divided by endurance limit when there is notch is present. Fine. So then if that is the case, I can write that Kf is equal to maximum stress sigma max divided by nominal stress. Then that maximum stress will be sigma f into nominal stress, and this maximum stress will be nothing but the actual stress acting in the actual component subjected to fatigue failure. You have to take this fatigue stress concentration factor into account. So the actual stress value is given by Kf into sigma naught. Is it clear?
Yes, sir.
We know that fatigue failure of a component arises due to a presence of discontinuity or a flaw in any material. So if flaw is there, if discontinuity is present in the material, definitely stress concentration will also take place. If stress concentration will take place, then I know that stress concentration factor, which is a measure of stress concentration, is given by Kt is equal to sigma max by sigma nominal. Then the maximum stress, that is, or then the maximum stress or the actual stress present in any component due to stress concentration will be Kt into sigma naught, and that is the value of theoretical stress, that is Kt into sigma naught. Is it clear? Any doubt so far? Hello.
No, sir.
Okay. Next, what is the definition? Definition of notch sensitivity factor is increase of actual stress over nominal stress. Nominal stress is sigma naught. Actual stress is Kf into sigma naught. So how much is the increase of actual stress over nominal stress? It will be Kf sigma naught minus sigma naught. Yes or no? Hello. Increase in the stress will be actual stress minus the nominal stress. Actual stress is Kf sigma naught minus sigma naught. Is it clear? Hello. Hello. Can you hear me?
Yes, sir. Yes, sir.
Okay. Similarly, I have to find out the increase of theoretical stress over nominal stress, which is due to stress concentration. So I know that nominal stress is sigma naught and theoretical stress due to stress concentration is kT into sigma naught. So how much is the increase of theoretical stress over nominal stress? It will be kT sigma naught minus sigma naught. kT sigma naught minus sigma naught. Yes or no? Yes or no?
Yes, sir.
Okay. So now we can write that stress concentration factor Q is what? Increase of actual stress over nominal stress. And increase of actual stress over nominal stress is Kf sigma naught minus sigma naught divided by increase of theoretical stress over nominal stress, and increase of theoretical stress over nominal stress is kT sigma naught minus sigma naught. So Q is equal to Kf sigma naught minus sigma naught divided by kT sigma naught minus sigma naught. You can take sigma naught common. If you take sigma naught common, it will be sigma naught Kf minus 1 divided by sigma naught Kt minus 1. Sigma naught cancel. Your stress that is notch sensitivity factor Q is given by Kf minus 1 divided by Kt minus 1. If I cross multiply it, I will get Q into Kt minus 1 equal to Kf minus 1, or I can write Kf is equal to 1 plus Q times of Kt minus 1. So if I know the value of stress concentration factor in any particular material, if I know the value of notch sensitivity factor Q, then easily I can find out the value of Kf. Or if I know the value of Kf, if I know the value of Q, I can find out the value of Kt. Or if I know the value of Kf and Kt, then I can find out the value of Q. This is the relationship between fatigue stress concentration factor, notch sensitivity factor, and stress concentration factor. That is Kf is equal to 1 plus Q times of Kt minus 1. Is it clear? Any doubt so
Yes,
far?
sir.
Any doubt so far?
Clear, sir.
Okay. So this you have to remember while solving the design problems related to fatigue failure. Next. So we know that the relationship between Kf, Kt and Q is what? Kf is equal to 1 plus Q times of Kt minus 1. Now this particular equation is valid for certain conditions. What are those conditions? Condition number 1. When material has no sensitivity to notches. That means when there is no notch, because when a material is having no notch, definitely there will be no sensitivity. Yes or no? If neither a single notch is present in any particular material, definitely there will be no sensitivity. Yes or no?
Yes, sir.
When there is no sensitivity, then which value in the given expression will be 0? When
Yes,
there is no sensitivity, which expression will be 0? Q will be 0. If there is, because Q is what? Q is notch sensitivity factor. It is the measure of sensitivity of notches. When there is no sensitivity, that means value of Q, that is notch sensitivity factor, is 0. So if Q is 0, then this entire term, that is Kt minus 1 into Q, this is 0, because 0 into Kt minus 1 is 0. That means Kf is equal to 1. Is it clear?
Yes, sir.
So this is applicable only when material is not sensitive to any kind of notches, which is practically not possible. Ideally, it can be possible, but practically it is not possible. What is the second case? Second case is when the same material is fully sensitive to notches. Any material will be fully sensitive to notches when there will be a notch present in the component. Yes or no?
Yes, sir.
So if a component is subjected to notches, that means there will be a sensitiveness of that notch. If sensitiveness of notch is present, that means the notch, if the notch is fully sensitive, then in the given expression, what will be the value of Q? Value of Q will be 1. Q can vary from 0 to 1. Notch sensitivity factor can vary from 0 to 1. 0 means there is no sensitivity. Value of Q equal to 1 means the material is fully sensitive to notch. If the value of Q is 1, then I can write Kf is equal to, I can write this Kf is equal to 1 plus Q is 1. That means Kt plus minus is minus 1. 1 cancel. That means Kf is equal to Kt. That means when material is fully sensitive to notches, then fatigue stress concentration factor will be equal to stress concentration factor. Is it okay? Any doubt so far?
No, sir.
No, sir.
Okay, so remember, you cannot blindly use this expression to design the component subjected to fatigue failure. Remember these conditions. You have to read the design problem very carefully. Then according to the conditions of the problem, you have to apply the formula. Okay. Hello.
Yes, sir.
Okay. So let us move forward. Next is the estimation of endurance limit. If you remember in the last lecture, I have told you this experimental procedure. With this experiment, that is rotating beam fatigue testing machine, we were finding out the endurance limit of a material. So can you tell me that if I use this experiment to find out the value of endurance limit of any material when it is subjected to fatigue failure, whether whether the estimation of endurance limit, will it take less time or will it take more time? Finding out of endurance limit of a material by this experimental method, will it take less time or will it take more time?
Less time.
Less time. कैसे less time होगा? From this experiment, you get this graph, you get this ascent diagram, and in ascent diagram, what you find out? You find out the value of endurance. You get the value of endurance limit at 10 to the power 6 cycles, because at 10 to the power 6 cycles, this line is exactly parallel to your x-axis, and the value of the stress value is almost exactly equal. So it is taking how much time? It is taking 10 to the power 6 cycles. That means 10 lakh cycles. That means you have to rotate this particular specimen 10 lakh times to get one endurance limit value. So will it take less time or will it take more time?
No, sir. It will take more time.
it will take more time. Fine, because if the material is rigid, if the material is hard, because you don't know that 10 to the power 6 cycles when it will come. It can come today also, it can come after 2 hours also, it can come, if that fatigue failure can come after 4 days also. You don't know. So it is, so by this experimental method of determining the endurance limit is a time consuming process. So normally we don't follow this. Most of the cases, in most of the time, we don't follow this particular procedure to find out the value of endurance limit. For that, what we do, we use some empirical relations to get the value of endurance limit. And those empirical relations are, assume that SE dash, this is what? This is your SE dash. This is SE dash. This is endurance limit stress of a rotating beam specimen subjected to reversed bending stress in Newton per mm square. That means this is that value of endurance limit which we obtain from the experimental method that I have discussed in the last class. And what is SE? SE is the endurance limit stress of a particular mechanical component subjected to reversed bending stress. SE is what? SE is the endurance limit value of any mechanical component. And what is SE dash? SE dash is the endurance limit value of a rotating beam specimen for which we find out from that rotating beam fatigue testing machine. So if you see that particular experiment, which we have discussed in the last class, in order to find out the value of endurance limit of a specimen, there is a particular length of the specimen, that is 85 mm. There is a particular diameter of the specimen, that is 7.5 mm. There is a particular fillet radius of the specimen, that is 250 mm. But in industry, it is not necessary that every time the length of the specimen will be 85 mm. It may be possible that in industry, the length of the specimen can be 100 mm, can be 200 mm, can be 250 mm. Yes or no? Yes or no?
Yes, sir.
So in that case, so this experimental method is only possible when the length of the specimen is 85 mm, dia of the specimen is 7.5 mm, and fillet radius of the specimen is 250 mm. But in industry, this may not be the case every time, because you are producing many components in the industry, and each component is having different length, different diameter, different fillet radius. So that's why we normally don't use this process to find out the value of endurance limit. So we use which process? This empirical process. In this empirical process, SE dash is what? SE dash is the endurance limit of the rotating beam specimen, which we find out from that particular experiment. And what is SE? SE is the endurance limit stress of any particular mechanical component. Then, if the material is steel, for example, you are making a shaft, and if the shaft is made up of steel, then this SE dash, that means the endurance limit value which you find out in the laboratory, that will be given by 0.5 times of SUT. If the material is cast iron, if the material of say a gear is cast iron, then that laboratory method of finding out the endurance limit value, that is SE dash, will be given by 0.4 times of SUT. If the material is wrought aluminium alloys, then AC dash will be given by 0.4 times of SUT. If the material is cast aluminium alloy, then SE dash will be given by 0.3 times of SUT. Is it clear? Is it clear? Hello?
Yes, sir.
Fine, because this SE dash, if you see that experimental procedure, there is a particular length, dia, fillet radius. For that particular length, dia and fillet radius, you will get SE dash. But in industry, length, dia and fillet radius of any component can be anything. So you cannot use that process. So for that, what we have did, we have used some empirical relations, and these data are available in the design data book. If you see the data book which I have posted in the Google Classroom, these data are there. If you see that data book, these data are there. So for steel, SE dash is 0.5 times of SUT. For cast iron, SE dash is 0.4 times of SUT. For wrought aluminium alloys, SE dash is 0.4 times of SUT. For cast aluminium alloys, SE dash is 0.3 times of SUT. So you have to read the problem thoroughly, that the shaft or the gear or the spring is made up of which material. On the basis of that material, calculation of AC dash will vary. And these values of AC dash, no need to remember, it is given in the design data book. If you see that design data book carefully, the values of AC dash are given to you. Okay. Any doubt so far? Hello. Any doubt so far?
No, sir. Clear.
If that is the case, then there will be one relationship between AC and AC dash. What is AC? AC is actual endurance limit of any particular specimen that is manufactured in industry. And what is AC dash? AC dash is the endurance limit stress value of a rotating beam specimen that is found out in laboratory. And that relationship between AC and AC dash is what? That is given by the relation SE is equal to KA, KB, KC, KD, SE dash. What are KA, KB, KC, KD? These KA, KB, KC and KD are known as D rating factors. This Ka, Kb, Kc, Kd are known as derating factors. DERATING, derating factors. Because in the laboratory, if you find out the value of AC dash, this is for a particular component. But this AC is for a particular component that is manufactured in the industry. So definitely, if you manufacture any component in the industry, it will have some stress concentration, it will have some notches, it will have some flaws. So definitely, the value of endurance limit of a practical specimen that you manufacture in industry will be somewhat less from the ideal specimen that you test in the laboratory. And if you remember, in the last lecture I have told you that endurance limit is not a property of material. It depends on some factors. What are these factors? These are the factors on which it depends. Ka, Kb, Kc and Kd. If you multiply Ka, Kb, Kc, Kd with AC dash, the resulting value of AC will be little bit less then the value of SE dash. Why it will be less? Because this is for ideal specimen, endurance limit for ideal specimen. This is endurance limit for a real specimen. A real specimen is having many flaws, many defects, many stress concentration regions. So definitely the endurance limit value will be little bit less. How much it will be less? For that you have to multiply derating factors with the ideal endurance limit value that you obtain from rotating beam fatigue testing machine. Is it okay? Any doubt so far? Hello? Any doubt so far?
No, sir.
Fine. And these, what are the purpose of these derating factors? The purpose of these derating factors is to derate or to reduce the endurance limit of rotating beam specimen to suit the actual component. This is for actual component. This is for rotating beam specimen. So these derating factors will reduce the endurance limit of actual specimen than that of the rotating beam specimen, which is an ideal specimen. Okay. And how to find out the values of Ka, Kb, Kc, Kd, that I will discuss in the next class. I don't think enough time is left. So the determination of Ka, Kb, Kc, Kd, that I will discuss in the next class. So far whatever I have discussed, is it clear to all of you?
Yes, sir.
Okay.
Yes.
Yes,
Please
sir.
don't leave the class since I think Thursday you all are having your lab examination of this design practice lab. So I will tell you something. Fine. So please don't leave the class. Just give me a minute so that I can switch off this PPT. And whatever, see, I think Thursday I may miss the class since Thursday you are having your design practice lab exam from 9:30 a.m. to 12:30 p.m. So I will not get my regular first period which I am having on Thursday from 9:30 a.m. to 12 to 10:20 p.m. So sorry, to 10:20 a.m. So what I will do is that in order to compensate that Thursday's class, on Saturday I will take that class, that Thursday's class from 10 a.m. to 11:30 a.m. Will it be okay for all of you? Hello. Hello. Will it be okay for all of you?
Okay, sir.
Okay, sir.
Fine. Because
Yes, sir.
the thing is, okay, just let me stop recording.